Two planets that orbited the Sun 3.5 billion years ago may have had biospheres of comparable size. Earth evolved in a way that made it possible for life to increase and fragment into an infinite number of exquisite forms. Mars, the other planet, took a different course. Welcome back, everyone. In today's video, we will discuss how an underground civilization on Mars could be. Remember to subscribe to our channel. Now, let's begin. The surface of Mars is known to be hostile. Yet, according to this scientific theory, Mars formerly supported a great plethora of bacteria. These organisms might have developed in crevices and cracks, reproducing until their total mass surpassed the stock of life because they were protected from the planet's fatal radiation and living in the briny underworld. The bacteria that lived on Mars, known as methanogens, would have breathed in air, hydrogen and carbon dioxide, and exhaled methane gas. In an ironic twist, these methanogens may have ended up becoming their own worst enemy. Their ever-increasing appetite would have eventually drained the Martian atmosphere of hydrogen, a potent greenhouse gas in the planet's early days, causing the planet to eventually experience a lethal cold and drive microbial communities into deeper, warmer crevices. It is unknown how long those bacteria may have persisted in the deep. They might have been a fleeting glimmer of life on an otherwise lifeless planet. The interior of Mars might not be as lifeless as its surface. It might be home to a world of extraterrestrial life that can wait thousands of years between each use of its metabolic engines. Even the most resilient Earth's bacteria would struggle to survive on the dry and radioactive Martian surface for more than a few seconds. However, the Earth was warmer and more aquatic billions of years ago. It needs to be clarified how long those temperate conditions persisted or how much water there was. Still, it's also obvious that ancient Mars had all the elements necessary for life as we know it, including organic compounds containing carbon and chemical reactions actively generating energy. Computational ecologist Sauteré decided to investigate the possibility of early Mars habitability. Before this, his team created models to describe how Earth's early life affected the planet's surface conditions about 3.5 billion years ago, when Mars may have also been habitable. Sauteré and his colleagues considered several Mars simulations with various atmospheres, surface temperatures, and brine kinds with various freezing points. They believed that any life on the planet would have been the same type of hydrogen-eating, methane-producing microbes that also inhabited early Earth. They also believed these microbes would only be found in environments at least 10 feet below the Martian surface, where radiation is rare and life-sustaining brines are abundant. The research team discovered that the type of brine and surface temperature significantly impacted the chances of habitability. In the team's simulations, a colder, more ice-covered planet was less likely to have habitable subsurface conditions because glaciers restrict the quantity of hydrogen gas that can penetrate the subsurface and power alien metabolisms. Sauteré discovered that there was at least a 50% possibility that portions of the shallow subsurface were habitable on a warmer and less icy globe in its most life-friendly form. The researchers discovered that Hellas Planitia, a vast impact basin in the planet's southern hemisphere, could support life in all but the most adverse conditions after mapping the planet's most likely habitable subsurface spots. Among the more hospitable areas were Ascites Planitia and the nearby Jezero crater, where NASA's Perseverance rover gathers materials for return to Earth. Sauteré and his team then simulated the Martian methanogens' potential impact on their environment. They were shocked to learn that life on Mars might have drained the atmosphere of planet-warming hydrogen due to its existence. Earth escaped that fate due to the different composition of gases in its atmosphere. These fatal Martian bacteria may have relocated even further underground, where it's warmer and more habitable, but less energy-rich, Sauteré and his colleagues speculate. They utilized fairly conservative definitions of habitability according to Jackie Gordile, a microbiologist who studies bacteria in the permafrost at Earth's poles. So life may have been much more likely to exist than the models suggest. The team, for instance, considered minus 20 degrees Celsius as the lowest temperature at which life might exist. However, Gordile notes that researchers have found evidence of bacteria existing at even lower temperatures on Earth. Additionally, Sauteré's team believed that the extent of habitable environments would be constrained by ice cover, preventing access to atmospheric gases. However, since microbes on Earth can consume hydrogen produced underground, it is possible that Martian microbes could exist deeper than the simulations predict. The third group of scientists investigated the possibility of life on Mars by observing how long bacteria could endure in environments that closely resembled those found about 30 feet below the surface. Although the soils are frozen and dry, the level of incoming solar and cosmic radiation at that depth is roughly equivalent to the dose sustained on Earth's surface. One of the most well-known extremophile bacteria, Deinococcus radiodurans, was chosen by the team for study because of its propensity to resist extremely high radiation doses. D. radiodurans found in nuclear reactors and Antarctic soils survive by swiftly repairing radiation damage to its DNA. In liquid culture, it can withstand doses of about 25,000 gray, whereas humans and most other vertebrates are killed by just 5 gray. According to a study published in Astrobiology, the group examining D. radiodurans discovered a way to make the creature even more extreme. A culture was first dried out. The culture went into a latent state due to being frozen, simulating the icy, parched state beneath Mars. They discovered that cells in suspended animation could resist a dose of almost 140,000 gray when they exposed the sleeping bacteria to increasing radiation. A shocking figure was determined by Daly and his colleagues when they assessed the life length of a cell of D. radiodurans living approximately 30 feet below the surface of Mars. To eradicate the cell would require about 280 million years. That figure refers to asleep cells, but over time, numerous warming occurrences, such as meteor strikes, could briefly change the subsurface environment and bring the cells back to life, giving them a chance to reanimate and proliferate. Similar severe life cycles in bacteria that are deeply buried beneath the Earth's surface have been discovered by researchers. And scientists have been able to recover live microbes from old permafrost cores. According to Gordile, models of life in deep-sea sediments also imply that some creatures may be able to thrive with very minimal energy input. If microorganisms are present, they are buried too deeply to be discovered by existing technology. Daly and his co-workers estimated microbe survival times at depths 100 times greater than the Perseverance rover's drill. Scientists intend to send Mars-bound spacecraft with deeper digging capabilities in the future. Although it wouldn't launch until the 2030s at the earliest, the Mars Life Explorer has been listed as one of the top priorities in American planetary science for the upcoming decade. Well, that's all for this video. We'll be back soon with another informative video. Remember to like, subscribe, and share. Until next time, we'll see you in the next video.